how advances in simulation are transforming AV and ADAS testing. I'm Kevin McNamara from a company called Parallel Domain. We develop simulation software that's used primarily for testing and development of autonomous systems. We'll talk a lot about that today. But this software is primarily used for simulating sensors like camera, lidar, or radar, and creating all of the interesting scenarios and content that you would need for testing autonomous systems. So I want to start with the motivation for why we do what we do. It takes billions of miles to make an autonomous vehicle, but it can take one bad mile to ruin it, right? And we've all seen examples of accidents out in the real world, testing and validating autonomous vehicles. The industry goal is to avoid those. So how do we make sure that those bad miles happen in something like a simulation so that we can make the system safe before we go put it out on the road? So this is the motivation for why we do what we do. And so what's the problem? Why might it be difficult to fix all of these issues ahead of deploying to the real world? Well, one of the main issues is that testing, especially autonomous vehicles, is a very difficult and slow process. In many cases, for an engineer to know how their software change may affect system performance, they may actually have to go put that vehicle on a test track. They may have to go put that vehicle on a road with a safety driver. And this is very slow. This can take days or weeks to get an understanding for how your software change actually impacted system performance. And when you have a really long feedback loop, that means your development process is much slower. For anybody here who's a software engineer, if your code took days to weeks to compile, you would not be able to develop very good software, right? Your code needs to compile quickly. You need to be able to test things quickly. That's exactly what we need for autonomous system development. And when that testing is slow, less testing happens, right? If it takes days or weeks to test your system, it means you're just not going to test as much as you really want to. Even if you want to test more, it's prohibitively slow, expensive, difficult to scale to do that. So ultimately, that means lower test coverage, right? If you're testing less, then you're not going to have the coverage you really want. But what if we could test at the speed of software, right? What if we could shift that testing from real-world tracks into simulation? So the ideal workflow would be that the software developer makes a change, they're able to scale that into a simulated test suite and get at least a first-pass understanding for how their system is performing in minutes or hours rather than days or weeks. Now, this isn't final validation, right? It's a first line of defense to understand how the system might be performing so that you can sort out a lot of issues before you then go take the time to get to the track. So ultimately, faster iteration on your autonomous system means safer vehicles, and that moves us towards the goal that we started at the beginning of the presentation. So a traditional development cycle, especially if you're training and testing ML models, can take weeks or months where you're collecting data, you're putting vehicles out into the real world, you're labeling that data, you're training models, you're then testing those models. That development cycle can take weeks. With simulation, we aim to do hundreds of iterations in that same amount of time. And what we're going to advocate for in this presentation is augmenting your real-world testing with software, right? So software augmented testing is really what we're aiming for. And wouldn't you rather have 100 iterations on that software rather than one in the same amount of time? So this brings us to the main topic of the presentation today. Simulation has evolved drastically over the past few years. What we're able to do in simulation today is quite different from just a few years ago. And primarily, we're going to be talking about digital twin simulation. So the latest 3D reconstruction techniques have enabled us to take real-world data from driving logs, flight logs from robots that are out in the real world, and reconstruct 3D environments. With those 3D environments, we can do physically based sensor simulation. So here you see a fully virtual simulation of camera, lidar, and radar running in a digital twin in an alleyway in Sweden, for example. The real data for this digital twin was captured by driving a car down that road, but we're then able to re-simulate new sensors, new actors, new actions inside of that environment, all inside of the simulation software. The idea here is to evolve this into a closed-loop simulation stack so that we can test an autonomous system's performance in a virtual copy of a real place. right? So instead of having to actually go to that road, go to that track, go to that alleyway, and test your new software in a car, you have a virtual replica of that. You have a digital twin of that place to test in simulation. Advancements in hardware and the ability to scale this up in the cloud means we can test thousands of virtual cars at the same time rather than having to reserve time at a track or get physical vehicles out there. So I want to do a quick walkthrough of how simulation technology has evolved to get us to this point, and then we'll talk about some of the impact that's having. So there are a couple of eras in simulation. The first is the human training era. Back in the mid-1900s, flight simulators really revolutionized pilot training. Over 500,000 US pilots were trained on simulators between essentially 1930 and 1950. From this human training era, we moved into a digital era. That's where a lot of things like crash testing was able to move into software, or at least be augmented by software. So in order to understand crash test safety, we didn't have to wreck a car every single time we wanted to run a new test. Maybe we would only do the physical crash test after we've run a bunch of simulations and had some confidence that the system was going to perform well. This did show that simulation can replicate reality closely enough to be an extremely useful part of the development process. But there was a big limitation here. This is very domain-specific simulation. Crash tests like physical deformation and finite element simulation doesn't really scale to the types of AI testing and validation that we need today. So there were some limitations in terms of how this could be applied to generalize outside of crash testing. That brings us to the next era in simulation, which I would probably mark as roughly 2005 through maybe 2015, which is the video game era. Using video game and graphics engines to create simulations that were certainly richer and higher fidelity than what existed before. And this made simulation more interactive, more scalable, easier to visualize what's happening. There's pretty wide adoption of these kinds of techniques within autonomous vehicles and ADAS companies. But there are some big limitations to this technique. The first being that fidelity gaps, realism gaps, mean that the results don't always transfer to real-world performance. As you can see in this image, you can see that this is a street with cars and people, but it's not realistic looking enough to train and test systems directly on that kind of data. So there's a domain gap there that is very difficult to solve using traditional techniques. The other problem with this approach is that it's not scalable. To create more and more of this content, you need lots of 3D artists. You can try to lean on something like procedural content generation, but you need highly qualified programmers to write those algorithms. And it turns out it's pretty much impossible to write a procedural algorithm to generate the entire world. So there's scalability and fidelity problems with these old approaches. Over the past few years, we've really seen the technology evolve to what we would call the AI and data-driven era. We're now taking data from the real world, making a data-driven simulation using 3D reconstruction and AI models. Half of the images that you see here are synthetic simulations, half of them are real. It becomes very hard to tell the difference between these. And there are the stop sign that you see in the middle left image, for example, is a fully synthetic stop sign that was not actually there. And so we're able to recreate these simulations with a much higher degree of fidelity now. And that's actually driven from real data. So that solves a few problems. This enables us to create a baseline from a real drive and then re-simulate new scenarios inside of that. It significantly decreases the domain gap that we mentioned on the earlier slide. This data is now much more faithful and realistic to what you observed in the real world. And the second piece is that you can control what's happening inside that simulation. So it's very scalable. We're going to show examples in a minute of adding jaywalkers into a real drive, changing the lane change behavior from a real drive. And these new variations enable you to scale the amount of simulation that you're running quite broadly beyond what was possible before. And so what we're seeing is simulation, especially virtual simulation for autonomous development, is really evolving from sandbox experimentation to a proving ground, to a virtual proving ground for autonomy. And lots of our customers are starting to adopt this at a production scale, running these simulations every day. So to dive a little bit more into what's new on the technology side with this new data-driven simulation era, this is an example of how we take real-world driving logs. This is a street in San Francisco. And now here is a re-simulation of that log. that this resimulation didn't have any of these actors that are in the scene originally. Originally, it was just an empty street. And as this car drives down the street, we're able to use the simulator to insert, there's actually a moose at the end of that street. Now there's a mail truck. Now there's a jaywalker. Now that jaywalker is a child instead of an adult. Those are all programmatically controlled through the simulator. Here we're showing examples of different types of digital twins. This works across domains. So we now have customers doing this for autonomous driving, but also for agriculture and autonomous tractors, for delivery, both aerial and sidewalk delivery, and for warehouse automation. This kind of simulated replication is a lot more than just a 3D reconstruction for visual use. We're reconstructing physics collision meshes, semantic information about the scene, material estimation about that scene, so that we can do a couple of things. So that we can resimulate a bunch of different sensors. So from just camera captures, we can create a reconstruction and then simulate lidar and radar. On top of that, we can insert physics-based agents. You can drop objects on the ground. You can have people walk across the streets. You can have cars collide against things. So all of this extra metadata that we're creating in the reconstruction process allows us to simulate physical processes, both sensor and non-sensor. And so as a reminder, the process that we're trying to accelerate is it takes a software developer days to weeks to go put something on a track and test it. Can we make that virtual? The idea is, well, what if you just made a copy of that testing track in simulation? So here's an example of M-City in Michigan, a fairly well-known real-world testing track. A lot of our customers test their vehicles here. This is a simulated fly-through, as you can probably tell from the camera movement. That is created by just driving on the track and collecting real data. And then this is the simulated replication of that. We're now simulating camera, lidar, radar inside of that testing facility. We're simulating multiple cameras at the same time. All of this is programmatically controlled. So adding a new camera is just a new line of code within this digital twin. And so ultimately that enables our customers to test quickly in software rather than in the real world. And then you only spend time on road once you've solved the problems that you should have detected and solved in simulation, right? It's just like programming. You quickly get hints from your development environment, whether or not you've made a typo, whether or not a variable exists or not, right? You find out right away if there's a problem. Only once you've solved those simple problems do you move to deploying your software. It should be the same thing for autonomy. You should get a quick understanding in simulation of how your system is performing, and then go put it on the real track afterwards. So the idea here is test without leaving your desk, right? Be able to test that system virtually right in simulation. Control the tests you need. You have faster development cycles because of this. You can replay and alter recorded drive logs. And difficult cases, like we see here, the Euro NCAP suite, where we're actually colliding with the back of a car that's in a road, we can now replay these in simulation. It's the same scenario, but copied and pasted on replicas of real places. This is Germany, Tokyo, US, multiple different locations here, all running the same scenario, but on different roads, right? So what if you could take that Euro NCAP suite that you typically have to go to the track to test and actually replicate it in every place you've ever driven? And the idea is that you would do this in a closed-loop simulation. So you're regularly monitoring and tracking how your system is performing. Every time you make a code change, how do you rerun those scenarios on every street so that you understand if you introduced a regression, so that you understand if you actually solved the problem that you were trying to solve. And this really helps people gain a quick understanding of how their system is performing. So here we want to talk about what is the common workflow to actually accomplish this, and whether you're doing this with our software or whether you're using some other simulators out there. We generally would recommend the same workflow. First, you start by reconstructing a digital twin from drive logs, and you're seeing that happen in the video here. You go and drive in a real location, whether that's your test track or a public road. From that drive log, you create a 3D reconstruction. That reconstruction, as we mentioned before, has enough information, needs to have physics information, needs to have enough visual information to then be able to resimulate sensors and physics. But with that, you can resimulate with variations. You can start to insert new agents. You can control the agents that you already captured and move them around. And then you can generate sensor data. So camera, lidar, radar, sonar, near infrared, thermal cameras. You can simulate those types of sensors inside of these environments and actually feed that data back into your autonomy stack so that you're forming a closed loop for testing. Here's an example of creating a digital twin from an open data set, from the Wave Scenes data set. So the input for this is just a single drive down this road, a van that had a bunch of cameras on it. From that, our system is able to recreate the environmental digital twin, but then insert new actors and agents driving, walking, and participating in that world. I haven't mentioned this part yet, but all of this is controlled through a Python API. So you can write code that programmatically controls variations and creates new actions and behaviors inside of that environment. Here's an example of doing that. So we're going to build a testing suite for jaywalkers, for example. So what you're going to see here is a bunch of different people walking across the street at different angles. And then we're going to copy and paste that logic across a bunch of different locations. So the input to this was a bunch of driving data where there were no people at all, or there could have been people, but they weren't jaywalking. And through the simulator, we can use the Python API to actually insert new pedestrians walking through that street, right? So the idea becomes, instead of trying to drive around in the real world and find examples of people jaywalking across the street, how do we take the drive logs that we have and make every single one of them a jaywalking scenario? How do we take the drive logs that we have and make every single one of them an emergency vehicle scenario by inserting an ambulance, for example? Another example would be lane change variation. And the videos may be a little small here to see, but we wanted to show a lot of variations. Here's a car driving down a replica of Highway 1 near Pacifica, not too far from here. That car is just driving straight in its lane in the initial scenario. On the bottom, we have 8 different lane change variations that have been generated through the simulation software to test how the driver might behave when there are different car configurations. So here's a fairly standard from right to left lane change with nothing in the way. That's enough. Here are 2 different examples now where the car actually has to speed up or slow down to fit in and merge behind or in front of traffic. Here's an example where we are actually making the car much, much more aggressive, and it's going to cut off this police car and merge right in front of it. I'm going to play all the examples here on the bottom where we continue to generate more variations of how that car might weave into traffic. So when you take all of these variations, we have an ability to generate a whole wedge of different behaviors from one initial drive log. So you're taking one drive log and you can create tens, hundreds, maybe even thousands of variations on top of that. Now we could test how our autonomous system might change lanes on Highway 1 at this specific exit with programmatically controlled traffic configurations. That becomes really interesting for autonomy development, where this would be near impossible to do in the real world. I can get to the next slide. I mentioned this a few times, but I do want to highlight one of the advantages of this 3D reconstruction approach is that you can simulate multi-sensor rigs. So here again is that digital twin of the M-City testing facility. This was captured using just a couple cameras mounted on a car. The M-City team actually went out and captured that data. We're now resimulating a totally different set of cameras. These were not the cameras that were originally on the car. You'll also notice that we're simulating lidar in the center view here. There was no lidar on that car originally either. So we're able to, by having the physical approximation of the geometry and materials and semantics of the scene, we're then able to simulated versions of active sensors like lidar and radar. There we go. We have a lot more material online. I would recommend checking out our website and our LinkedIn. Michael, who's also here, you can talk with him at our booth afterwards if you want, has done some really interesting work around recreating real-world failure cases. There was this example video from a YouTuber named Mark Rivera who took a Tesla and a bunch of other cars and drove them at a cartoon Looney Tunes style wall, right? What if you paint a brick wall? What if you paint a road? Is the car actually going to hit the brakes? We actually could recreate that in simulation and show that standard off-the-shelf perception systems that are camera only make exactly the same mistake because they mistake the painting on the wall for depth. But as soon as you add a lidar sensor, for example, the lidar is going to immediately see that that's a solid wall, and the perception system hits the brakes instead. So there's really interesting ways to recreate failure cases that you might care about inside of simulation as well. As I mentioned, we have a bunch more of these kinds of examples online. So, back to the development process. This whole idea of augmenting your real-world testing with simulation and accelerating your real-world testing with simulation, it's something that we call shift left, right? So typically, testing and validation in the real world happens towards the end of the development process, where you've built most of the system components, you're finally getting a car out onto a real road, you have all the hardware and software loaded onto that car. Often that testing happens very late. It doesn't happen at the scale you want it to, and it's very difficult to control the conditions you want. But with software augmented testing and simulated testing, you can shift that process left. You start testing much sooner. You start building your test coverage much sooner. You're getting immediate feedback on how your system is performing every day or every week throughout that process. This is how modern software development works. Autonomy development shouldn't be any different. And you can see, kind of the before and after here. The idea is that you're also testing a lot more, right? The area under these curves is much larger when you start testing earlier and start testing inside a simulation. So a couple of quick lessons of working with customers in the field on this. As I mentioned, we've got people doing drone delivery, ADAS development, autonomous vehicle development, autonomous tractor development. They're all using these kinds of digital twins on roads and farms and backyards for actually testing their systems in simulation. What we're finding is that setting this up as a daily regression testing system is extremely valuable, right? You may have anywhere between 1 and 500 engineers working on your autonomy system. They're making a lot of changes throughout the day. If they could kick off a automated regression testing simulated suite at the end of the day, come back in the morning to a report as to how the system performed, that's a ton of extra insight on how the work that they did the previous day may be impacting system performance. And a lot of autonomy developers don't have that today because they would have to actually go put vehicles out on a test track or out at one of their testing airports, for example. Some of our customers are even running this as a CI/CD workflow every couple of hours. When submits get committed, the tests kick off and they rerun. Sometimes they even have that as a gating factor to release. You have to pass a suite of tests before your PR can actually be accepted. So ultimately, simulated testing can lead to frequent early detection of problems. That's extremely valuable. But also real-world testing is critical for final validation of a system, right? There still is some degree of domain gap between simulation and the real world. Now, as we talked about today, the technology advancements have really drastically closed that gap, even in the past 24 months. But the combination of these two together, we think, is the most powerful. And that's why we really advocate for combining them. We're not advocating that you replace real-world testing with simulation. We're advocating that you start simulated testing much earlier and you use that to augment your real-world testing. So that's why we say software augmented testing. So physical testing typically stops when the track closes. Simulation never sleeps. And the idea is that you can run simulation while you are sleeping. So the idea is that you finish your work at 5 p.m. at the end of the day and you submit a suite of simulated tests, and that's going to run overnight. You come back in the morning and you have a result. Use that time where software can be doing this testing for you. And so to recap at the end, software augmented testing combines the best of both worlds. Ultimately, the goal is that faster development iteration means arriving at production quality sooner. Why do one iteration when you could do 100 inside of software and then do your real world iteration after you've sorted out the problems in software? So to rewind to the very beginning, this is the motivation for why we are advocating for software augmented testing and simulation. It takes billions of miles, if not at least hundreds of millions of miles, to make a good AV, and it takes one bad mile to ruin it. We want to make sure those miles happen in simulation. So thank you, everybody. I think we have probably 2 minutes. If there's 1 or 2 questions, I'd be happy to take them, but we also have a booth there. You can come chat with us after. Thank you. Yeah, perfect question. So he was asking, what's the correlation between the simulated world and what you see in the real world? How do you bridge that gap? Ultimately, we want to be able to trust that the sim we run is indicative of how the system would perform. So one of the really big advantages of this kind of digital twin approach is that we start with a drive log. So often what we do with our customers is we take a collection of drive logs where they have real world observed performance, right? They've driven down a street, they've recorded that data, they could feed that data into their autonomy stack and test it, right? How did our perception system perform, for example, on this real captured log? So now we have an indication of how the perception system performs on the real data. We take exactly that real data and we create a digital twin and recreate that same scenario and see how the system then performs on the simulated data. So simulate the lidar, simulate the radar, add the cameras, make sure that the behavior of those two systems is within some tolerance. If you start to do this over enough different scenarios, you start to build up a statistical confidence that the simulated behavior is correlated well enough with the real world. We've got some blog posts on this, so at paralleldomain.com/blog. We've done some benchmarking on this, but we'd love to talk more deeply if you'd like to at the booth just behind us. Cool. Thanks, everybody.
This is it.
Thank you, too.